Hi everybody. So here's my problem assignment video. The course I've selected is my college pre-calculus course. This is a CIS class. And the learning target I decided to work with here is that students can use exponential growth and decay functions to model and solve real-life problems. Um, these are a lot of really fun problems to work with when we're using exponential growth and decay functions. Specifically, I want to talk about Newton's law of cooling and how I could turn this into more of a problem-solving um, task for my students. So, um, my hook, how I'm going to get my students interested and drawn into the problem is usually when I talk about Newton's law of cooling, I bring up something like, hey guys, last night we were at home, my family and I were having supper, we made some pizzas, I took the pizza right out of the oven, I cut it up, and I took a bite right away, and what happened? And they'll say, you burned your mouth. I was like, yeah, I burned my mouth, and I thought of you guys. And then you get them to chuckle and laugh and think about, okay, what does he mean he thought of us? And I start to kind of draw them into this concept that we got to let the pizza cool, and how do we let that pizza cool? How does it work? Things like that. And then I bring up um, that Isaac Newton described the cooling process for objects when they are placed into a new environment as an exponential decay function. And I tell them that he wrote this law of cooling, but I'm not going to tell them what the formula is. Now, here is the old version of the problem and how I would work through it. I would put this problem on the board and we would get started. A pie is taken out of the oven with an internal temperature of 165 degrees Fahrenheit. It's placed on the kitchen counter where the room temperature is 70 degrees. After 10 minutes, the pie is cooled to 120 degrees. If we want to wait until the pie is cooled to 90 degrees before we eat it, how long will we have to wait? So in the past, I've done this problem together. And a few things happen with this that I think are good and that we learn from them, but I'm going to adapt this and I think make it even better for the future. So typically what students do is they've looked at exponential growth and decay functions. They have a familiarity with it. But all of the exponential decay functions that we've looked at have had a horizontal asymptote of the x-axis, that they have approached zero. So usually what I do is I let the students drive our work together on this, and they tend to want to throw our 165 degrees as our y-intercept, as the initial value that's in front of our exponential base e, and then we work through it, and they usually forget completely about the room temperature being 70 degrees. They set up the problem and work through it, and they get something. Then usually what has to happen is I have to say, well, what could we do this? Let's look at the graph. Let's see what the temperature looks like over time. And then we pull up the graph, and the graph will surely show that the temperature is approaching 0 degrees as time continues on. And it usually takes a minute or two before somebody recognizes that. And then we rework the problem, figuring out how do we handle this new horizontal asymptote of 70 degrees. So that's how I used to do it. Now, to make this more of a problem-solving task, I'm putting more on the students. Here's my new problem and my new setup. So what I would do is I would put this problem on the board, and I would have my students work in groups of 3 at the whiteboards around my classroom to answer this question. So the difference in the question is that what will the temperature of the pie be after 30 minutes? So on the previous question, I said, how long do we have to wait before it's 90 degrees? Now, the reason I am switching this to be what will be the temperature of the pie after 30 minutes is I think more students will recognize the common mistake that is made, because after 30 minutes, if you work this through, the temperature will be less than 70 degrees. It'll be like 61, something like that. I don't have that written down. I did it already, but you'll get an answer like 61 degrees, and I think students will catch on the fact that that's not reasonable considering the temperature of the room is 70 degrees. So my plan would be to post this problem on my board and have my students work on it in groups, and hopefully they will be able to recognize that they have to do some adjusting for the new horizontal asymptote of 70 degrees. And I'm really excited to see if they can come up with that on their own, where in the past, this is something that I had to drive the conversation on. Okay, new horizontal asymptote, how do we do that? And then there's a lot of places that we can go with this. I can go to the remove the numbers and come up with the formula for Newton's law of cooling. I can state, okay, these are what I want you to call the variables. Can you come up with the equation? Then we can do questions like the first one and ask how long do we have to wait before an object reaches a certain temperature, and we can have a lot of fun with that. So there's my new problem solving task for my students, taking it off the whole group and the instruction from me and placing it on them, making a little twist to hopefully make them recognize that they have to change the horizontal asymptote.